Last time, we saw how Johannes Kepler came to believe that the motions of the planets were governed by physics, that there is a force steering them in their orbits, and that this force originates in the sun. With this insight and the superb observational data of Tycho Brahe, Kepler devised three mathematical laws describing the orbits of the planets: the law of ellipses, the law of equal areas, and the harmonic law. But Kepler never knew what kind of force the sun exerted on the planets. He compared it to light or to magnetism. He wondered whether it might have something to do with the rotation of the sun. He thought it might be something very mysterious. Well, 50 years after Kepler's discoveries, the real answer was found. And the man who found it was Isaac Newton. The mysterious force that steers the planets is not really all that mysterious. It is the most familiar force of all, the same force that pulls the apple down from the tree. The stars in their courses are steered by gravity. Isaac Newton was the greatest scientist of his age, maybe the greatest scientist of all time. It is impossible to exaggerate his contributions to mathematics, to mechanics, to optics. For a century, physics was essentially a series of footnotes to Newton's great work. When Newton died, the poet Alexander Pope wrote an epitaph for him. Nature and nature's laws lay hid in the night. God said, "Let Newton be," and all was light. But my favorite story about Newton occurred a bit earlier. In 1696, the Swiss mathematician Johann Bernoulli published a really clever and tricky math problem, and he challenged the mathematicians of Europe to solve it. Well, at the time, Newton was warden of the Royal Mint in England, and he came home after work at the Mint, he read Bernoulli's problem, and he stayed up late to solve it. The solution by Newton was published anonymously, but Bernoulli was not fooled. Bernoulli said, "Ex ungue leonem," that is, we can tell the lion from his footprints. What we want to do in this lecture is follow in Newton's footprints, not to solve Bernoulli's math problem. What we want to do is start with Galileo's discoveries about motion and Kepler's laws about planetary motion and arrive at a far-reaching new framework for physics. And it all begins with an astounding insight into the nature of gravity. Now, to explain that insight, we have to return to the apple. In Lecture 1, we heard one version of the story of Newton and the apple. And now I'll tell you another. This is the version that Newton himself told to his friend William Stukeley near the end of his life. It starts out the same. Newton is sitting in an orchard, and he sees an apple fall down from the tree. In this story, though, the apple inspires a very different train of thought. Newton asks, why does the apple fall down? That is, toward the center of the earth. Why that direction out of all the possible directions it might move? What is special about the center of the earth? What gives that point in space a special apple-pulling power? Newton realizes there is no such special power. Or rather, that is a power that is shared by everything in the universe. He says every part of the earth pulls at the apple. It is pulled to one side by the ground over here. It is pulled to the other side by the ground over there. It is pulled by parts of the earth that are close by and parts that are far away. And maybe the far-off parts pull less because they're so distant, but there are also more of them in total. And what is the net result of all those forces? The total pull on the apple is straight down toward the center of the earth. That is to say, the side-to-side forces cancel each other out, but generally, the downward forces add up. So in other words, Newton says that this force of gravity is a universal property of matter. Every piece of matter in the universe, however small, however distant, exerts a gravitational pull on every other piece. Of course, large pieces of matter exert a greater power of attraction, and large pieces of matter are also pulled more strongly by other pieces. After all, the Earth's gravity pulls me with a greater force than it pulls the apple. Newton calls this idea the law of universal gravitation. Now, this is one of the boldest hypotheses ever proposed, but Newton backs it up with careful mathematics. So let's suppose that we have two particles. A particle is just a physicist word for a small piece of matter. And we'll call them particle 1 and particle 2. They have masses m1 and m2 respectively, and they are a distance r apart. Then Newton says that they are attracted to each other with a force F equal to g times m1 times m2 over r squared, where g is a universal constant of nature. We'll call it Newton's constant. Now, whenever we see an equation, and especially a really important one like Newton's law of gravity, we want to take a minute to appreciate it. First, what force are we talking about? Well, this is the force that pulls particle 1 toward particle 2. And an equal force, a force of the same size, pulls particle 2 toward particle 1. So more about that in a few moments. Second, note that the force of gravity depends on both masses. Larger masses exert greater attraction, and they experience greater attraction in turn. Third, note that we divide by the square of the distance r. The larger the distance between the particles, the weaker the force of attraction F. And the square is the interesting part. So if the distance doubles, the force goes down by a factor of 2 squared, that is to say 4. If the distance is increased by a factor of 5, the force is less by 5 squared. It's 25 times less. And finally, note that there is a constant g that determines how strong gravitational forces are. So, just how big is Newton's constant? Well, in fact, Newton himself never quite knew its actual value. As we will see in Lecture 5, that question requires us to do a very delicate experiment, but we'll anticipate somewhat. The value of Newton's constant is g equals 6.67 times 10 to the minus 11th meters cubed per kilogram second squared. Now, the units I've given to g look a little funny, but they make everything work out. The point to note is that this is a small number. If you write it out as a decimal, you'll have the decimal point, followed by 10 zeros, and then 667. And that means that gravity is a remarkably weak force. And we mentioned that fact back in Lecture 1. Okay, so much for the gravitational force between two tiny particles. What about the gravitational force between big objects like stars, planets, and moons? Well, here Newton discovered something amazing. So suppose you consider the force of the whole Earth on the apple. The Earth is composed of zillions of tiny pieces of matter distributed through a huge volume of space. Some pieces are close by, some pieces are far away. Each piece exerts its own pull on the apple. But Newton showed that as long as the Earth can be regarded as a sphere, the net result is exactly as if the entire mass of the Earth were located exactly at the center of the Earth. So we can use Newton's law of gravity to calculate the force exerted by the Earth on the apple. So if big M is the mass of the Earth and little m is the mass of the apple, and r is the radius of the Earth, then an apple at the surface of the Earth is pulled with a force F equal to g times big M times little m over r squared. That's exactly as if the whole Earth were one massive particle located a distance r away, that is to say, located at the center of the Earth. Okay, what about the sun and the planets? Newton realizes that the planets are steered in their paths by the sun's gravity, that is to say, a force that pulls each planet toward the sun. Now that sounds a bit strange at first. Kepler seems to have believed that the sun's force actually pushed the planet along in its orbit. But Newton knew better. After all, as Galileo told us, if no force were to act on a planet, then its property of inertia would carry it along in a straight line in space. So the actual force from the sun does not push the planet along, it would go along a straight line without any force. The force is the thing that bends its path. So in what direction does it bend? It bends toward the sun. So the force that deflects the planet from a straight line path is a force that pushes toward the sun. This is true anywhere along the planet's orbit. The path of the planet is always bending toward the sun. The simplest case is when the planet's orbit is a circle. The force that steers the planet in that orbit is a centripetal force, a force that is directed toward the center of the circle. That force is the force of gravity exerted by the sun. Now, this does not result in the planet getting nearer to the sun. In a circular orbit, it stays at the same distance. But as it follows that circular orbit, it continually turns toward the sun, pulled in that direction by the sun's gravity. So, Newton gets the essential idea back in 1666, but it takes him 20 years to work out the details to his own satisfaction. It's not easy. He has to invent the whole subject of calculus just to handle the mathematics. But at last, in 1687, he publishes his book about motion and gravitation, Philosophiae Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. This is a landmark, an epic of physics. It's one of the greatest works of genius in all of human history. So what is in the Principia? Well, it contains Newton's theory of gravity, of course, but to use that theory to understand motion, Newton also introduces 3 general laws of motion, the foundation of mechanics, which is the science of force and motion. So, Newton's first law of motion is just Galileo's law of inertia. In the absence of an external force, a body maintains a constant velocity. Thus, a body at rest will tend to remain at rest, and a body in motion will tend to remain in motion in a straight line, so long as there is no external force. A force would cause a change in velocity. So how does that work? Well, for that we need Newton's second law, the equation of motion. We call it the equation of motion because we can express it by a simple equation. F equals m times a, where F is the net force on a body, m is the mass of the body, and a is the resulting acceleration of the body. There are several things that we should note about Newton's second law. The equation of motion contains some qualitative information. Suppose we apply a particular force, F, to an object. Then a small body with a small m will have a large acceleration a. But a large body with a large m will have a small acceleration a. That's why it's easier to push the grocery cart when there's nothing in it. But think about it this way. Mass is a measure of the inertia of an object. It tells us how much it resists changes in its velocity. So if an object is not accelerating, then the net force on it must be 0. But that 0 might be the result of several forces acting in different directions. For example, consider me standing here. The force of gravity is pulling me downward. But the floor is also pressing upward against my feet. And those 2 forces add up to 0, which is why I am not accelerating either up or down. Finally, consider the units of measurement for the terms in the equation. Mass is typically measured in kilograms. So here's a mass of 1 kilogram, a 1 liter bottle of water. Now, acceleration is the rate of change of velocity, so it's measured in meters per second. That is often written meters per second squared. And we saw in lecture 2 that the acceleration of a freely falling object near the Earth is about 10 meters per second squared. So the units of force must be kilograms times meters per second squared. The combination is called 1 Newton of force. And that means that the gravitational force on a 1 kilogram object in our classroom is about 10 newtons. You might be familiar with another unit for force, the pound. A pound is actually a unit of force. We often use it as a measure of the weight of an object. But weight is a force, the force of Earth's gravity on an object. So if you want to calculate your weight in newtons, you need to multiply your weight in pounds by about 4.5. There are 4.5 newtons in 1 pound. Okay, so consider a falling apple accelerating downward due to the gravitational attraction of the Earth. The force of gravity is F equal to G times big M times little m over r squared, where m is the mass of the Earth and little m is the mass of the apple, and r is the radius of the Earth. Now let's combine this with Newton's second law, the equation of motion. And we get that m times a, the acceleration, equals g times big M times little m over r squared. Notice, the mass of the apple, little m, appears twice in this equation. On the left, it comes from the equation of motion. On the right, the same factor comes from Newton's gravitation law. But they are the same mass. We can just divide by it and get the acceleration of gravity. A equals g times big M over r squared. This is the acceleration that physicists call little g, the acceleration of gravity near the Earth. And in lecture 2, we saw that this equals about 10 meters per second squared. Now, note well, this acceleration depends on the mass of the Earth, big M, and on the radius of the Earth, r, but has nothing to do with the particular falling object. It would be the same for an apple or a banana, or a professor, or a big cannonball, or a small cannonball, or a hammer, or a feather. In other words, Newton's theory gives us Galileo's law of free fall. All kinds of objects near the Earth's surface fall with exactly the same acceleration. I like the equation of gravitational acceleration because it lets us figure out how strong gravity might be on another world, on our own moon, or a giant planet like Jupiter. So let's take a minute to do that. Now, we could look up some precise data about mass and radius and use a calculator to get exact figures, but I think it is more fun and actually more revealing to make the kind of approximate calculation that we can do for ourselves. So what about the moon? Well, the equation tells us that the acceleration of gravity is proportional to m over r squared. Now, m and r are both smaller for the moon than for the Earth. The mass is about 80 times smaller, and the radius is about 4 times smaller. And that means the numerator goes down by a factor of 80, but the denominator also goes down by a factor of 4 squared, or 16. Now, it happens that 80 is 16 times 5, so that tells us that the acceleration of gravity on the moon is about 5 times less than it is on the Earth. So, how did we do? Well, our approximations were a little off. The gravitational acceleration on the moon's surface is closer to 1/6 g than 1/5 g. But that's not too bad, and we never had to touch a calculator. All right, how about Jupiter? Well, Jupiter is 300 times more massive than the Earth, but it also has a radius 11 times greater than the Earth's radius. Now, actually, Jupiter is a gas planet and has no real solid surface, but this is its visible radius, the radius of the tops of the clouds in the atmosphere. So, the gravitational acceleration there will be multiplied by 300, but divided by 11 squared, or 121. So 300 divided by 121 is just about 2.5. And that's right. An apple on Jupiter would fall with an acceleration of about 2.5 g. That's an interesting number because it is curiously small. I mean, after all, Jupiter is huge. It has hundreds of times the mass of the Earth. Yet its surface gravity is only 2.5 times greater. The reason, of course, is that the surface of Jupiter is so far from the center of Jupiter. Those two factors, larger mass and larger radius, work in opposite directions in the equation. Or, to put it in physical terms, Jupiter does have a lot of mass. If you are at Jupiter's surface, all of that mass is pulling on you. That's universal gravitation. But Jupiter is so huge in size that a lot of its mass is actually very far away. So the net gravitational pull is less than you might expect. Now, sometimes this can lead to surprises. So Saturn, a gas giant planet like Jupiter, has about 100 times the mass of the Earth. But it is also about 10 times the radius of the Earth, and 10 squared equals 100. So the two factors pretty nearly cancel out. The surface gravity on Saturn is about equal to the surface gravity on Earth. An apple on Saturn would fall at about 10 meters per second squared. And in fact, if you do an exact calculation, you find the acceleration of gravity on Saturn is actually slightly smaller than on Earth. Okay, after the law of inertia and the equation of motion, we reach the last of Newton's laws of motion. Newton's third law, the law of action and reaction. So if an object A exerts a force on object B, then object B exerts a force on A that is equal in strength but opposite in direction. Now, in many ways, this is the really brilliant and subtle one. This is the one that nobody before Newton had quite understood. And this principle has some amazing consequences. We'll mention some of those in Lecture 6. For now, I want to point out how this law is related to Newton's idea of universal gravitation. So to put it in a nutshell, if the Earth exerts a gravitational force on the apple, then the apple also exerts a force of the same size, on the Earth. When the apple falls down toward the Earth also falls up toward the apple. Now, that equal gravitational force produces a much smaller acceleration for the Earth, which is a few trillion times more massive than the apple. But the force is there. Everything exerts gravitational attraction on everything else. In the Principia, after Newton has formulated his laws of motion and of universal gravitation, he draws some wonderful conclusions. Most importantly, he is able to apply his laws to the orbits of the planets. The mathematics is very difficult, but Newton is the lion, and in the end he is able to derive all of Kepler's laws. He finds the orbit of any planet around the sun should be an ellipse with the sun at one focus. He finds that a line from the sun to the planet should sweep out equal areas in equal times. He finds that the semi-major axis of an orbit, cubed, is proportional to the orbital period, squared. Kepler derived his laws by analyzing Tycho Brahe's observations, and with the assistance of his own keen intuition. And his foremost intuition was that the orbits of the planets were shaped by some kind of force acting from the sun. Now Newton proves that Kepler had it exactly right. The simple universal law of gravity acting between the sun and the planets automatically produces motions of exactly the kind that Kepler discovered. It is a complete triumph for Newton and a vindication of Kepler. And that's not all. Newton does not just prove Kepler's harmonic law, he improves it. Kepler's harmonic law related the orbital period p of a planet to the semi-major axis a of its orbit. The equation was a cubed equals k times p squared, where k is the same constant for all the planets. Now here is what Newton finds. If a planet orbits the sun with an orbital period p and a semi-major axis a, then a cubed equals g over 4 pi squared times m times p squared, where m is the mass of the sun. Pi, of course, is the familiar number 3.1415, the ratio of the circumference to the diameter of a circle. So that is, where Kepler had an arbitrary constant in his proportionality law, Newton has an exact equation. I sometimes like to call this Newton's 1, 2, 3 law. Mass to the first power times orbital period to the second power is proportional to semi-major axis to the third power. It's an amazingly useful equation. Why is it so useful? Because we can use it to determine the masses of distant objects in space. Think about it. We can observe P and A for some planet, and that will let us figure out M, the mass of the sun. Or we can look at Jupiter's moons orbiting their planet according to the same laws. By determining the sizes and periods of those orbits, we can figure out M, in this case, the mass of Jupiter. And we can go further. Many of the stars we see are actually binary stars, in which one star orbits another. More precisely, the two stars orbit each other, moving around a common center. By studying their orbits, we can use the 1, 2, 3 law, Newton's improved version of Kepler's harmonic law, to calculate the masses of the stars. And this is a basic technique for determining the mass of objects that are far away from the Earth. But of course, the technique depends on two things. First, it depends on measuring distances so that we can find the value of A, the semi-major axis, for a distant orbit. And two, it depends on knowing the value of Newton's constant, g. Those two things are a lot harder than they may sound. So before we learn more about Newtonian gravity, we're going to have to take a look at just how those things were determined. We're going to take a look at some of the cleverest, most careful observations and experiments ever performed. And that is a story worth telling. And in our next lecture, we will tell it.